Hello everyone, welcome back to the channel. In this video, we will be discussing about the last problem of today's weekly contest, count the number of ideal arrays. So this is a little bit harder than usually the last problem. So keep patient and I will be I can guarantee that you can get the solution at the end. So let's start. The problem states that you are given two integer n and max value. Uh, and you need to count the number of distinct ideal arrays. What is an ideal array? Ideal array is defined as the array where every value is between 1 and max value, and for every array of I, it is divisible by array of I minus 1. So for example, 2 4 is an ideal array because max value here is 5, so 2 and 4 both are less than 5, and 4 is divisible by 2. Similarly, 1333 is an ideal array because everything is smaller than or equals to 3, and if you can look at any two adjacent element, they are divisible by, they are divisible. So this 3 is divisible by 3, again 3 is divisible by 3, and 3 is divisible by 1. So this is what an ideal array is. Now for a given n and a max value, you need to find out ideal array of length n, like all the distinct ideal array of length n. And since the answer can be very large, you have to return it modulo 10 to the power 9 plus 7. So hope the problem is clear. Now let's try to solve it. Now before solving, we have first constraint is very simple. The first constraint state that the value should be between 1 and max value. So this constraint is very similar, like we just need to take care that every element that we pick is lesser than or equals to max value. The interesting piece is the second constraint, wherein it is saying that array of I should be divisible by array of I minus 1. So there are multiple p's in the problem. First, we need to find out array of length n, right? So first, how will you fill this array of length n? Let's say first you need to pick what all elements will you take, okay? And second, you need to choose how to fill those elements in the given length of array, because you can see 1333 is also a valid array. So if you choose 1 and 3, then also you need to find out how you will fill this part in the array, okay? So there are two unknowns, okay? Let's try to solve each of them one by one. Let's start with the second one, how to fill elements with elements in the array with length array of length n. So let's assume that we already know the elements which we want to fill in. Now we just need to find out how many ways are there to fill that particular element. So for example, if let's say we are already sure that we need to fill in 1 2 and 6, okay? So you need to you know that you need to fill in 1 2 and 6. So you have an array of length 6. Now how you will fill this 1 2 and 6 in array of length 6? The thing is, you will just start with 6. Let's say you put 6 again, you put 2, you put 2, you put 2 here, and you put 1 here. This is one possible valid arrangement of these numbers. So notice that for a given set of integers, there is only one order that they can be filled in. So for example, we have 1 2 and 6, right? So there, you can't actually fill in 2 before 6. There is no possible valid solution in which 6 would come before 2. Similarly, there is no possible valid solution in which 1 would come after 2. And similarly, there is no possible valid solution wherein 1 will come after 6. So basically what we are seeing here is, for a given set of integers, there is only one possible way, one possible arrangement to fill these integers in, and that arrangement is in increasing order. So we know that we need to fill in 1 2 and 6, and these integers we have chosen such that they are divisible, like they are already satisfying this condition. Like that's the only condition that we want to achieve. And for this condition we have these two constraints. So we are currently saying that let's just assume that we know the element somehow, and now let's just find how many ways are there to fill this particular set of elements in the array. And for that, what we are seeing is, for a given set of integers there is only one possible way to fill this array in. So that's our first observation from this exercise, that for a given set of integer there is only one order in which they can be filled in. So for example, in this particular case there is only one order. Like first you will put all the ones, then you will start with 2, put 2's in some boxes, and then you will start with 6 and put 6 in some boxes. So there is only one order they can be filled in, and this order is actually increasing order, because you know that they are like 6 should be divisible by 2, so you have to put it in increasing order. Now let's say that you have to fill this three integers, right? Now what about, like okay, first let's try to see some of the possible solutions. So these are like some possible ways to fill this integers 1, 2 and 6. So we start with putting 1 in only one section, then we start by putting 1 in 2 boxes, then we put 1 in 3 boxes, and then we put 1 in 4 boxes. Okay, now if you note here, let's say there are total t number of ways in which 1, 2, 6 can be filled in these 6 boxes. Now do you think that this t will differ if we want to fill 12, 6 and 3? Like let's say if the integer set is 3, 6 and 12, do you think the total number of ways to fill 3, 6 and 12 in these 6 boxes would be different than t? The answer is no, right? Because thing is, you are able to fill 6, 2 and 1, and you know that this can be filled in increasing order. There is only one way. You will put 1 in the first, then 2 in the first, then all the 2's, and then 6. So similarly for 3, 6 and 12, what you can just assume that 3 is equivalent to 1, 6 is equivalent to 2, and 12 is equivalent to 6. So in a way, what you are saying is the number of ways is independent of the actual integers that you are trying to fill in. Again, because, like, why is this true? This is true because the order in which you will be filling in the integers is fixed. There is only one order in which you can fill this in integer. So because of this constraint, what we are able to see is that what we are able to see here is the number of ways to fill x set of x integers in independent of the elements present in the set x, right? So it doesn't matter that if you want to fill in 1, 2 and 6, or you want to fill in 3, 6, 12, or you want to fill in 100, 10 and 1, everything, unless it has 3 integers and you have to fill 6 boxes, this will be the value, like number of ways would be t only. Okay, so in a way, what is our problem now? The problem is now reduced to, we have to fill the array of length n such that the array is increasing and every element should be less than x. So this you can ignore, like we already assume that every element is less than x. So array is increasing and all the elements from 1 to x should be present. So here x is basically the largest. So again, we have 3, 6 and 12. Let's say we also have 1, 10 and 100. So all these things are similar, right? So instead of saying this 3, 6, 12 or 1, 2, 6, let's say them 1, 2, 3. Like number of, if we have to fill 3 integers, let's say those integers are 1, 2 and 3. Like just we are mapping this 3 to 1, this 6 to 2, and this 12 to 3. Okay, now if we said that, then array should be increasing and all the element from 1 to x should be present. Basically 1, 2, 3 should be present. So this we need to just find out how, like, to find out how many ways, like, remember how we start with the question, how many ways are there to fill in this array of length n. So now we are trying to find out how many ways are there to fill the array of length n, but the constraints is now you have to fill the array in increasing order, and all the elements up to, like, from 1 to x should be present. So let's try to solve this problem instead. Okay, so this is our problem. Now we have to fill the array of an integer with this constant again, like, just cross it. So now let's just see all the elements from 1 to x should be present, right? And the array should be increasing. So what does it denotes? It denotes that the last element should be x, right? No matter what you fill in the previous elements, last element should be x, because all the elements should be present and the array should be increasing. So last element will be x. Now if last element is x, what is the problem now? The problem now reduced to filling up an array of length n minus 1 with integer 1 to x. So in a way, we are trying to solve the same problem again. Previously we have a length of, like, array of length n, and we have to fill in it with 1 to x, where every element from 1 to x is present. Now we have an array of length n minus 1, and we have to fill in this array of length n minus 1 with integers 1 to x, where x can or cannot be present, because x has already occurred, right? So now there are two things, x can and cannot be present. So this problem is not exactly similar to what we are trying to solve, right? So let's just try to convert it. So let's say that this problem can be converted to fill array of length n minus 1 such that you have everything from 1 to x. This is one piece, and array of length n minus 1 such that you have everything from 1 to x minus 1. This is second piece. So basically, when we fill x here, we are saying that we need to fill in the rest of the n minus 1 array such that everything from 1 to x should appear. But now, because we have already filled in x, so x may or may not appear in this remaining array of length n minus 1, right? So that's where we've broken this, like, case into two cases. First case where we say that, okay, we have to fill the array of length n minus 1 such that everything from 1 to x will occur. Even though x occurs here, we are saying that x will again occur. And second case where x will not occur anywhere in this array is this. We have to fill array of length n minus 1 such that everything from 1 to x minus 1 should be present. So now this two problem is exactly similar to the original problem that we are trying to solve, right? So this two problem is exactly similar to this problem, just with reduced constraints. Previously we have to fill the array of length n with elements from 1 to x. Now we need to fill the array of length n minus 1 with elements from 1 to x. And second problem is we have to fill the array of length n minus 1 with elements from 1 to x minus 1. So this problem is exactly similar to the previous problem, hence you can see a recursion here. So the simple pseudocode for this would be something like this. Okay, so what, like, we have to fill in the array of length n with everything from 1 to x present, like 1 to x should be present. So we start with, like, if there is nothing in the, like, nothing to be filled, like array length is 0, we just see that we have something to be filled. Let's say there is no array at all, like there is no length at all, and you are saying that you have to fill everything from 1 to 5. Is it possible? No, right? Because there is no place at all to fill in. So that's where we are checking if x is 0 or not. Like x equals to 0. If x is also 0, then we will return 1, otherwise we will return false. Now, this is the base case. Now the, like, main case that we have discussed, we will fill in x at the last position, like at the nth position we will fill it. This is the nth position, let's say. So we will fill in x here. Now for the remaining n minus 1 position, we will break it into two parts, that we make sure that x again occurs in the left, and if x again occurs in the left, it will be unique arrangements n minus 1 to x, like we have to fill n minus 1 elements with everything from 1 to x. Now, second case is x will not occur in the left anymore. So in that case, we will just fill all the n minus 1 elements with 1 to x minus 1. So finally, we will just return answer. And remember, we need to memorize it to make sure that we are not calculating the same state again and again. So this piece, like with this piece, what we have just solved, let's just look at the broader picture again. So we have started with two unknowns. The first unknown was which element should we take, because we don't know, like we have to take elements such that they are divisible, right? Like remember, we can't take 1 to 3 actually. We have to take 1 to 6 or 1 to 8. Like basically everything that should be divisible by each other. So first problem was that how to take that element, and second problem was how if we have taken that element, then also we are seeing that there are multiple possible arrangements for a single set of elements. So how many ways are there to fill in those particular set of elements? So for this problem, like we have skipped the first problem for now, and for second problem we have just found a solution. This is the pseudocode for that. What we have done, like in a very brief, what we have done is we have said that okay, it doesn't matter what we are trying to fill, whether we are trying to fill 1, 10, 100 or 10, 100,000 or anything like that, unless we are trying to fill three elements in a given set of n indices, the number of arrangements would be similar. How we have figured out, just rewind the video and watch that. Once we have figured out that, we can just say that how many unique array, like we can just map this 1 to 10 to 1 to 3, and we can just say that we have to fill in the array with everything from 1 to 3 such that everything is increasing. Now for this is the pseudocode that we just discussed, simple recursion. Now what is left is how many like which element should we take now. So in a way, what we have just figured out a while back is it doesn't matter what the actual sequence is, like what the actual numbers are. It only matters how many, like what is the number of distinct elements in this number, right? Like in this sequence. So basically we can rename this, or we can just remake this problem to something like how many sequences of length x, or how many distinct sequences of length x that can be formed from values to 1 from 1 to m, right? M is max value in the question. So basically we have figured out that it doesn't matter how many, like what all the numbers are, it just matter how many unique numbers were there in the sequence. So we can just figure out how many distinct sequences of length x are there that can be formed from 1 to max value. So now let's try to solve that piece instead. So what we are trying to solve now is how many unique sequences of length x that can be formed. So for that, before solving that, let's just focus on how many sequences of 20 can be formed. Okay, so let's say we have 20. So what all things do you have? You can just like you can go from 20 to 10 by dividing it by 2. Like basically 10 is divisible by, so 20 is divisible by 10. So you can just remove one factor from 20 and it will become 10. You can remove 4 from 20, it will become 5. You can remove 5 from 20, it will become 4. And similarly, you can remove 10 from 20, it will become 2. And you can remove entire 20 from 20 and it will become 1. So in a way, what this tree denotes that starting from 20, how, like where all you can reach. So starting from 20, the immediate next children are 10, 5, 4, 2 and 1. Now starting from 10, again there are various possible scenarios. You can take 2 from 10, and then you can either take 5 from 10, or you can take the entire 10 from 10. From 5, there is only one possible scenario. You have to take entire 5 from 5. For 4, again there are two possible scenarios. You can either take 2 or you can take the entire 4, and so on and so forth. So basically what we are seeing here is we are like for a particular number, we are forming a tree, and that tree will ends up at 1 every time. Okay, and with this tree we can simply find out how many unique sequences of length x are possible. So this is one unique sequence, right? Similarly, this is another unique sequence of length 3. Similarly, this is another unique sequence of length 4. So every path in this tree is a unique sequence, right? So now you can't actually enumerate all these paths because that would be very costly. So instead, what you can do is save some kind of computations. So you can see that there is 4 here, right? Like this is the expansion of 4. So this expansion of 4 is something that will be constant for every integers that will end up at 4. So let's say you are ending up at 4 from somewhere, like no matter where, from where you are ending at 4. So if you are ending at 4, you will be expanding it in this particular way, correct? So let's just try to use this, like basically expansion of 4 or expansion of any element will be constant. Let's just use this particular uh, trick to see if we can reduce the number of computations, because clearly you can't actually enumerate everything in this tree because that would be very costly. It will not fit in the time complexity. How costly we will look at, but that will not fit in the time complexity. You can't actually enumerate all these paths. So let's just focus on a single piece. Let's say you have expanded 4 already. You already know how many unique paths of 4 are there. Unique path of 4 are, there is one path of length 1 which consists of only 4. Then there is two path of length 2, 4 and 1 and 4 and 2. Okay. Then there is one path of length 3 which is 4, 2 and 1. So this is what you know for 4. Like this you already know. Okay. Now let's say you reach 4 from various places. Let's say from 20, 16, 28, 32, from these places you reach 4. So what you can say, how you can use this computation? So in a way, what you can do is, let's say you reach from 28 to 4. So in a way, what you can say that you are expanding 28 and you reach 4. So instead of expanding 4 further, you can simply take this computation and use it in your computation of 28. So what you are saying is, okay, I came to 4 in one step. So whatever lengths were there starting from 4, all these paths will have one more length because they will now start from 28. So in a way, starting from 28, you will find a path that has length 2. Like all the paths that have length 2 from 28 that will end at 4 would be increased by 1. Like how many paths were, like 28 can have more paths, right? So whatever paths 28 have, but from 4 it will get 1, because from 4 there is only one path of length 1. So from 28 there will be only one path of length 2, like basically containing two nodes, 28 and 24, 28 and 4, right? Similarly, what you can say that, okay, from 28 there will be two paths, this path and this path. There will be two paths that will go through 4. How like there will be two paths of length 3 that will go through 4. So similar, so you just add 2 in the length of 3. So hope you can see what we are doing. We are just we have introduced one edge, and with this edge what we are saying is we can just add this contribution, the contribution of everything here, to the original contribution or the total contribution of that particular element that we are trying to expand. So similarly, we will just add 1, 2 and 1, like to the length 2, 3 and 4. Similarly, like just again note that we are not adding 1 to length 1, because with 16 to 4 there is already one edge that is involved. So hence one node is already there. 16 is already there. So everything will be shifted by 1 and then will be added. So from 16 there will be, like from 4 there are two paths of length 2. So from 16 there will be two paths of length 3. Similarly from 28 there will be two parts of length 3. So hope this point is clear now. So just try to apply this again with 20. So while calculating 20, you will assume that you have already calculated 10, 5, 4, 2 and 1. Now once you have calculated all of them, now you're trying to calculate 20. So with 20, what you will see, you can just go through first level of children, 10, 5, 4, 2 and 1. This you can get from divisors, right? Now once you go there, you can just update 10, like contribution of 10 into 20, just shifting this contributions by 1. So whatever number of paths of length 1 was there in 10, you will add that in length 2 of 20. Whatever path of length 2 that are at 10, you will just add that many number of paths to length 3 at 20, and so on and so forth. So with this exercise, what you will have is, you will have the entire array of 20 built in. So what this array denotes, this ith position of this array denotes how many paths starting at 20, or how many paths are there which have maximum value of 20 are there, like how many unique paths which have maximum value of 20 are there. So for example, like you 1, 5, 10 and 20 is one such path. So you will get all the unique paths that has length x, right? You will get this. So basically you will, instead of like getting this x, you will be getting this x for each integers. For 20 you will get this x separately, for 4 you will get this x separately, and so on and so forth. So finally, how the pseudocode for this would look like, the pseudocode will be a lot simpler than the actual approach. What we are doing is, we are like, we have just said that for 20, from 20 we can go to all the divisor. So instead, let's just make it reverse. Let's say when we calculated the value of 10, we will go to all the multiples of 10 and update them. So basically, we calculated the value of 10, we calculated the array of 10. Now we go to 20, 30, 40, 50, 60 and update them all. So that's what we are doing. We are starting from 1. Okay, and then we are like, for 1 we already know the answer. Like if there is only one node with 1, the array will contain everything 0, just the first element will be 1, everything else will be 0, right? Because there is only one path of length 1 that is possible from 1, nothing else. So we will just start from 1, and we will update the multiples of 1, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and for every multiple we will update all its length. Okay, so just to give, give another example, like for one more example, let's say for j is 4. So if j is 4, you will iterate over 8, like 8, 12, 16, 20, 24, 28 and so on, and let's say you visit 16. So when you visit 16, you will add all the contribution of 4 to 16, just shifting by 1. So that's what you're doing. You are adding all the contribution of 4, like j is 4, so you are adding all the contribution of 4 to one shifted length, like one shifted position of 16. Like k is multiple of 4, which is 16 in this case. So you are adding this. Now once you have this loop ended, what you will be getting is an array. For every element you will be getting an array that will denote how many unique paths are there of length, like let's say you are talking about the index I. So how many unique paths are there that will be, like that have this particular number 28 as the last number and has length of I. Okay, so once you get this, you can just use this unique arrangement for every such path of length x and just multiply the number of paths that you have of length x, because again it doesn't matter which all numbers are there in length x. If the path is of length x, the arrangement will be same. So hope this entire solution is clear. Let's just quickly look at the code to make it more concrete. So what we have done is we have this unique arrangement that is exactly similar to what we have just looked at. Basically, it's saying how many unique arrangements are there of length and having all the values from 1 to x. Okay, so this is what unique arrangement denotes. And ideal array, and once you have you will have this unique arrangement and you will memorize it because you don't want to calculate the same state again and again. Now you calculated all the unique path length. This unique path length is exactly similar to what we have just discussed. We will just start with 1 and we will contribute this j to all its multiple. So we will contribute this j to all its multiple, just shifting one position. Okay, and once you have calculated all the unique paths, you will just iterate over the all the values. So remember that unique like lengths of j will contain how many lengths of jk. Okay, let's just write it down again. Lengths of jk denotes how many unique paths are there that ends at j and have length of k. Okay, so length of jk denotes this. So what you will do, you will just iterate over all such jk. So that's what we are doing. This j is last here and k is j here. So we are just iterating over all such jk, and for all such jk we are finding how many unique arrangements are there for a particular j. So this is j is the length, right? The length of the unique path. So what you are doing is you are finding out all the unique arrangements of length j, and you have to fill the array of length n. So once you have get this unique arrangements, you know that there are this many number of paths that ends at that is of length k. So you will just multiply this number with this length of last n j and add it to the answer. So I know this is little intense. I would, if you don't get the solution, I would strongly encourage to watch the video twice so that, and I'm sure you will get each and every step of this solution. If you have any doubts in the question, please post them in the comment section below. I will be happy to answer. If you like the video, give it a thumbs up and do share it with your friends so that they can also get benefited. Thank you.